We're going to break this Chapter 13, Section 1 into two parts. So we will call this 13.1a. 13.1a. And in this section, we're going to be talking about the dissociation of solutions and how the net ionic equations work with dissociation. So you got a lot of writing to do in this one, not really any math. So the term dissociation is the separation of ions that occur when an ionic compound dissolves. So we are looking at ionic compounds, breaking apart into their ions. I highly suggest that you have out your pink sheet that has your periodic table and all of your polyatomic ions on it. This is as refreshers. If you are still struggling on how to get charges of ions, things like that, and you need refreshers, make sure you reach out to me. So, sodium chloride in water. Sodium chloride will dissociate into the sodium and chloride ions. It's important that you get their charges correct. Sodium chloride is a solid, but once you dissolve it in water, the AQ means aqueous, so those ions are floating around in a solution of water. We have 1 mole of each of these because this is a balanced reaction. And in this one, calcium chloride can also dissolve in water to give you the calcium chloride ions. This has been balanced too. You can see the coefficients of 1, 1, and 2. Therefore, 1 mole yields 1 mole plus 2 moles, and we're looking at the coefficients there. If you looked at the dissociation of sodium chloride, you can see your water molecules have started to attach themselves to either the sodium ion or the chloride ion. Sodium being positive, it wants to attach itself to the negatively charged oxygen, and chloride ion being negatively charged wants to attach itself. I say attach itself, it's being pulled apart by the hydrogen of the water, which is positively charged. So those opposite charges that are attracting. So let's go through this problem right here. It wants us to write an equation for the dissolution of aluminum sulfate in water. And then it's saying how many moles of aluminum and sulfate ions are produced. What's the total number of moles of ions produced whenever you're dissolving 1 mole of aluminum sulfate. So that means we need us a balanced ionic equation once we are finished. So aluminum sulfate. I'll go and put my mark out here. Should be 2, SO4, 3. This is a solid state, so it is important that you put your states. It is dissolving in water, dissociating in water to yield aluminum ions. Aluminum has a 3+ charge. Again, it's in group 13. It's in solution. And sulfate ions, SO4 with a 2- charge. That's your sulfate ion in solution. If you go back and you balance this right here, you have 2 for the aluminum, you have 3 for the sulfate. And if we go into part A of the problem, part A, how many moles of aluminum and sulfate ions are produced by dissolving 1 mole of aluminum sulfate? Well, you have 1 mole here, 2 moles of aluminum ions, 3 moles of your sulfate ions. And if we look at the next part of the question, what is the total number of moles of ions produced when you dissolve 1 mole of sulfate? Well, 2 plus 3 equals 5 moles. That answers the second question. Please don't skimp on any of the writing, coefficients, charges, the state of the material, solid, liquid, gas, aqueous. Please don't skimp on those. Although no ionic compound is completely insoluble, meaning it will not dissolve or break apart, compounds of very low solubility can be considered insoluble for most practical purposes. And so how do you know if something is soluble or insoluble? We do have a chart that goes with that. This chart right here in the book that we're using, I will make copies of it for those that are in class. If you're virtual, it'll be referred to as figure 1.3. This will This chart is needed in your homework. I will also post it in Google Classroom for future use if you do not have a copy that I'm giving out in class. So general solubility guidelines here. These are just some of the more pronounced, obvious ones, more commonly used. These are not the only guidelines though. So number 1, sodium, potassium, ammonium compounds are soluble in water. That means they will break down into ions. Number 2, nitrates, acetates, and chlorates are soluble. 3, most chlorides are soluble except they list off silver, mercury, and lead. If you know anything about silver, mercury, and lead, those are considered to be heavy metals. So heavy metals are typically insoluble. Number 4, most sulfates are soluble except for barium, calcium, mercury, strontium, lead. Again, mercury, lead, more of your heavy metals. If I look at the barium, calcium, strontium, and strontium are all there at the bottom of group 2. Number 5, most carbonates, phosphates, and silicates are insoluble except sodium, potassium, and ammonium. Sodium and potassium, ammonium were listed there in 1. So 1 and 5 are going to complement each other. And then 6, most sulfides are insoluble except calcium, strontium, sodium, potassium, ammonium. So again, some of these are complements to others. In this picture right here, it shows some ionic compounds that are soluble or insoluble. You can see in the first 4 that are given here, these are not necessarily colorless solutions. Some of them have color to them, but they are clear solutions where things have been soluble. And in the last 2, those precipitates that you see at the bottom are going to be considered insoluble there. So AgCl and CDS are insoluble in water. We do have a lot going on in this one. I'm going to highlight some important parts for you. They are putting 2 clear colorless solutions together here. Sodium chloride, which is the sodium and chloride ions dissolved in water. And then you've also got your silver nitrate dissolved in water. So you have your silver and nitrate ions. And then finally, here at the bottom, once you pour those 2 together, and you have a solution here at the bottom, you will see a precipitate that is formed because the sodium in one solution, the silver, I got that backwards, the chlorine in one of the solutions, the silver in the other, did combine together to give you silver chloride, which is considered an insoluble salt. So we do have something called net ionic equations. These are going to be compounds and ions that undergo a chemical change in a reaction in a solution. And these ions that do not take part in the reaction are found in solution both before and after the reaction are called spectator ions. So the rest of this smaller piece of section that we're doing, we're going to concentrate on these net ionic equations. And we're going to be picking out spectator ions. We're going to be picking out what's considered soluble and insoluble. So there is an overall ionic equation here. You can see this overall ionic equation. Notice that we have our arrow over here. It's just too much to put on one particular line. But beforehand in solution, you've got cadmium and nitrate that were in solution together, ammonium and sulfide that were in solution together. And when you add those up, a precipitate is formed, CDS. So I am looking at the cadmium of one solution, sulfide in another solution that were able to mix together to give you the precipitate cadmium sulfide, but you still have ammonium and nitrate ions that are in solution. So those that are still in solution are considered to be your spectator ions. So they're just watching, seeing what's going on. They're not really involved in any of the reaction. So that's called your overall ionic equation. We've canceled out your spectator ions that appear on both the reactant and product side. So your net ionic equation takes out the spectator ions and leaves what I had highlighted. Cadmium and sulfide ions yielding cadmium sulfide, which is in the solid state because it will be insoluble in water. So know the difference between overall ionic equation, spectator ions, and the net ionic equation. Writing a net ionic equation, again, you have your chemical equation that you're going to work with, because chances are for the chemical equation it's going to be what we started off with at the beginning. So your true compounds that you have, your total ionic equation, you're breaking everything down into ions that can break down into ions. And then your net ionic equation will get rid of your spectator ions. Notice in my chemical equation there at the top, we had barium sulfate, that was our precipitate, that's our solid, back talking about double replacement reactions, and it's still in the solid phase down here too. So if you have something in the gas phase or the solid phase initially, they are going to stay intact. So before we get to the real sample problem of B, I've kind of skipped ahead a little bit, but things that we have to think about. You're going to write your equation for your double replacement reaction. You'll identify what the precipitate is in the double replacement reaction. This is what would be considered to be insoluble. You'll write your formula equation, your overall ionic equation, and then your net ionic equation. So we will go through all steps of that right now. So as we look at this, it says identify the precipitate that forms when an aqueous solution of zinc nitrate and ammonium sulfide are combined. Write the equation for the possible double displacement reaction or double replacement reaction. Then write the formula equation, overall ionic equation, and net ionic equation for the reaction. So first thing you have to do is you have to adequately, this is going back to chapter 7, predict what your products are going to be and write down your reactants appropriately. So zinc nitrate. Zinc has a 2+ charge, nitrate has a 1- charge. This is because they're all ionic, we're doing the crossover method here. So the 2 crosses over. The understood 1 would technically cross over, but we don't write the 1s. That becomes our new subscript. And you end up with zinc nitrate. And then for ammonium sulfide. Ammonium is NH4 with a 1+ charge. Sulfide is a 2- charge. And you cross those over because a 2 and a 1 do not cancel. Your final formula, NH4, the 2 crosses over. S, the 1 would cross over from the 1+, but it is not needed. So we write down zinc nitrate. And since it says they're aqueous solutions, that's AQ plus ammonium sulfide, AQ, and now we have to predict the products. In a double replacement reaction, it's always cation first, anion second, so you take the cation of one and the anion of the other, and you put them together. Again, this is based on charge, so cation here, anion of the other, and you put them together. So when I put zinc and sulfur together, zinc is a 2+ charge, sulfide is a 2- charge, so those charges cancel. You got Z and S. And then we got to figure out what's the phase. And then we have ammonium and nitrate. Well, ammonium's a 1+ charge, nitrate's a 1- charge. Those charges cancel. And we figure out what the phase is. So ammonium nitrate, I am looking back at my solubility guidelines or solubility rules, to figure 1.3. And I see that rule 1 says ammonium compounds are soluble. Well, that means the NH4NO3 has to be in aqueous solution. So AQ there. And then for the zinc sulfide, let's see here. I am looking at rule number 6, guideline 6. Says most sulfides are insoluble except, and it lists them off. Zinc's not an exception. So that must be our precipitate, which would stay in the solid phase. So you have to go through all of this work we have done before, know your ions, know how to cross over for ionic compounds, get proper formulas. If you do not get proper formulas, it's going to be near impossible to do the rest of this accurately. So make sure you know how to do those. So I've already gone through part A, which is we've given the equation for the double displacement reaction. There's your equation. We will identify the precipitate, which we have already identified the precipitate. So there's your formula equation. We've put in zinc sulfide is a solid, which was the precipitate. Ammonium nitrate is soluble, so it's in aqueous solution. Next up, so that's the formula equation. It also wanted the overall ionic equation. Now we have to break all of that into the ions. We just looked at the ions. There's your overall ionic equation. Again, zinc sulfide in the solid phase stays in the solid phase. It's insoluble. It cannot break apart. And then part E, the net ionic equation gets rid of our spectator ions. So nitrate is on both sides. Ammonium is on both sides. Our final net ionic equation is going to be zinc plus sulfide ions yields zinc sulfide. So again, a lot of writing, but make sure whenever you're given your homework or in classwork, you answer every part thoroughly.